Thank you for the introduction. But before I begin, I just wanted to take a moment and thank the organizers for allowing me to speak today and for organizing such a wonderful summer schooling conference. So that's all. So elliptic curves are really cool. I'm sure most of you would agree. And they've been of interest to mathematicians for a long time. They appeared in the writing of Greek mathematician Diophantus back in the 3rd century. So today I'm going to start by posing the following classical question. Given a polynomial equation, what are the rational solutions? So, for example, if we have the equation y squared equals x cubed plus ax plus b, where a and b are rational numbers, so what are the rational solutions? Now this polynomial will represent an elliptic curve if negative 16 times the quantity 4a cubed plus 27b squared is non-zero. So that's what we're going to start with. Now in 1922, we have the following result of Mordell. So we know that the collections of points on E with rational coordinates is a finitely generated abelian group. So notice at the bottom in the little box that we have a torsion part and a free part, where the free part consists of R copies of C, where R is the rank of E, which we know is finite for a fixed E. But today we're going to focus on the torsion part. So remember, a torsion point is a point of finite order. So we have this piece of information, and a natural next question to ask now is what finite groups arise? So in 1977, Barry Mazur completely classified the torsion subgroups that arise for elliptic curves defined over the rational. It's important to note that these all do occur. But so we have that. So we have over Q, the next logical thing is for quadratics. So in the 1990s, over a collection of publications by Kamiani, Kinku, and Momose, we have the classification for quadratic. So, all right, so what if d equals 3? So if we, why would we restrict to elliptic curves defined over quadratic or rationals? What about cubic? So result for t equals 3 has been announced, but the article has not yet been published. So almost a century after Mordell's proof that EQ is a finitely generated abelian group, we only have the complete classification for torsion subgroups arising over the rationals or quadratic. But we'd like to, consider all member fields and what else, what other classifications we have. That's what we'd like. So in 1996, Mordell proved that if we consider all elliptic curves E defined over F, and we allow F to vary over all number fields of fixed degree D, then only finitely many groups arise as torsion subgroups. So we want to consider extending the classification, but so we're kind of we're a little stuck. So one way to extend the classification is to restrict the elliptic curves under consideration. There are many different ways we can do this. One option is to look at elliptic curves E over Q under base extension. Others look at what groups occur infinitely often, or another option is to look at elliptic curves with complex multiplication, or CM. This third option is our focus today. So this talk focuses on extending the classification of what torsion subgroups arise for elliptic curves with complex multiplication. So what is CM? For most elliptic curves, we have that the endomorphism ring is isomorphic to Z. So we are adding a point P on our elliptic curve to itself in times, where n is an integer. But an elliptic curve has complex multiplication if its endomorphism ring is larger than Z. So it's going to have some extra structure. So we have So here we have where O is an order in an imaginary quadratic field K of conductor F. Just some notes on notation there. So let's look at an example. The elliptic curve y squared equals x cubed plus 1 has Cm by the maximal order and Q adjoin the square root of -3. But it also, you can check that this is an endomorphism. But notice this is not an integer multiple of the point. So it's extra, we have extra structure, and our endomorphism ring is going to be larger than Z. So if we're hanging out in CM land, which is a good time, we want to know what do we know about torsion in the CM case. So aside, what's been really cool is all these names that I'm about to list and tell you what we know about torsion in the CM case. I've gotten to see those names pop up during this online conference, which was really cool. Well, some of the names. So torsion for CM elliptic curves in 1974, a result of Olson is we have if E is a CM elliptic curve over Q, then the torsion subgroup is going to be isomorphic to one of the following 6 groups. Sometimes you see these groups referred to as Olson groups. In 2014, a result of Clark, Kornreis, and Stankiewicz, they completed the classification of torsion for degrees up through 13, which is cool. And then in 2015, work of Bourdon, Clark, and Stankiewicz completed the classification for prime degrees and for p squared degrees, where p is prime. Then in 2017, a result of Bourdon and Pollock, they completed the classification for odd degrees. So we have all the odds, all the primes, which go right in there, except for 2, and then up through 13. So the natural next question is what happens over a number field of degree 14? So that's where I started. So if we have a number field F of degree 14 and E is a CM elliptic curve defined over F, the torsion subgroup is going to be isomorphic to one of the following. Now, it's important to note that the groups that didn't arise in degree 2 are Z mod 29Z or 43Z or 49Z or 58Z, because we're looking at degree 2 times a prime, so 14 was the first unknown degree, and we've classified that. But we needed to do a few more degrees and kind of see what else we're getting. The reason I've listed the groups at the bottom that don't agree in degree 2, or that don't occur in degree 2, that's what I'm going to call new torsion. So instead of listing all of the possible torsion where some of it occurred in earlier degrees that divide, 14, so 2 and 7, I'm just going to list the new ones. So how did we do this? I call this my proof-ish. So one of the first things I used when I started trying to figure out a list of possible ends was a result of Bourdon and Clark of their 2018 work. If we have a CM elliptic curve E defined over a number field F of degree 14, it's going to have a point of order and it has a point of order n. Then we know that phi of n divided by the size of the unit group, that needs to divide 14. I put 14 here, but we could put D as well. That's their result. So this is how I start, by generating a list of some ends. And then this is a lemma that I found. If we have that phi of n divided by the size of the unit group, if that is equal to D, so in this first case, if it was equal to 14, then every prime that divides n needs to be ramified, or if we have the largest power of 2 dividing n is just like 2, 2 could be split, but other than that, 2 would need to be ramified. So with that piece, I have this list of ends from this earlier piece of information that I've generated. So then we can narrow it down a little bit. Don and Clark's work, 2009 work, they have much more explicit divisibility and least degree conditions. They're a little notationally heavy, so they're not very pretty. But so those also were able to help me narrow down some possibilities. And then lastly, we constructed examples. So if we look at that list again, 29, 43, 49, 58, we were able to construct examples. So, all right, we have 14, so what's next? We also are able to do some computations and find new groups occurring in degree 22, 26, and 34. Notice all of these are of the form 2 times a prime. But in degree 38, this is the first time we see no new torsion. So the only torsion subgroups that occur for d equals 38 also occur over a quadratic. So we say it has no new torsion. Now we've seen results that were stated in the papers earlier for when odd degrees and primes, we've seen no new torsion. But this is the first example of an even degree where we don't pick up any new torsion. So that was pretty cool. We classified the first unknown degree and we found an example of an odd degree with no new torsion. So, of course, the next step is let's go ahead and generalize this. So, if we have a number field of degree 2p, where p is a prime greater than 3, and E is a CM elliptic curve defined over F. If we have a new torsion subgroup and the J invariant of our elliptic curve is not 0 or 1728, then our torsion subgroup is going to be isomorphic to Z mod MZ for M equals 5, 8, 12, or 2p plus 1. Or it's going to be Z mod 2Z cross Z mod 2MZ, where M again is 2p plus 1. Now that 2p plus 1 needs to be prime. So we call a prime P a Sophie Germain prime if 2p plus 1 is prime. So there's more of this theorem for the other J invariants, but I finished this almost at the exact same time that Ken Rubik actually came to our school and gave the Gentry lecture. So it was really cool to get to see this 2p plus 1 that had appeared and then have a name put to it in connection to his contributions to the proof of Fermat's theorem. So it's a really cool day in math land for me. But let's continue the other pieces of this theorem. If the J invariant is 1728, and we have new torsion in, for degree 2p, then the torsion subgroup is going to be isomorphic to Z mod MZ or Z mod 2MZ, where M is 4p plus 1. But again, we need that 4p plus 1 to be prime. And then the last piece, my problem child, was the J invariant 0. So we're going to split that into two cases if we are not in degree 14. So as long as p is not 7, then the torsion subgroup is going to be isomorphic to Z mod MZ, where M is 6p plus 1. Again, we need 6p plus 1 to be prime. If p is 7, then we can have Z mod MZ be 6p plus 1, or it can be Z mod M squared Z for M is 7. The reason this ended up being a problem child is that when the J invariant is 0, the size of the unit group is 6. And so V of 7 is 6, and that's where all the stuff like it started over there. So those are my results. I wanted to say thank you for listening.
Hey, thank you.